Hey everybody, this is Larry. This is day 20th of the Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's daily problem. Single element in the sorted array. So, okay, you're given a sorted array, only integers that appear twice except for one element which appears exactly once. Return the single element that appear once, log n of one space, of course. Yeah, of course, I mean, so as soon as I read like this part, I was like, okay, well, the linear solution is just to go through the array, right? And it's sorted so you can find it very quickly. The single element will appear next to you, or in this case, not appear next to each other. So you can find that very quickly. And of course, that's linear time, constant space. But then, of course, my next thought was that would be too easy, right? Like, I mean, there are some easy Leetcode problems, but that'd be too easy. So that must be that we can do in log n time, and then next line, there you go. It have to be in log n time, and you can actually. The fun thing is that they can actually implement an interface so that they can enforce this log n time, but they don't. So oh well. But in any case, so yeah, so this is actually not that bad. It's just trying to figure out like an invariant, right? Some kind of property that is true, so that you can kind of divide the things in half every time. And the way that I actually like immediately thought is that, well, some variation on this, but then I refined it as I'm talking, is that, you know, if we kind of if everything is paired up, let's say we're not missing a number, right? Then if we pair it up, then we would have 0 index per se, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, right? And of course, that means that, you know, depending on how you want to index it or whatever, they'll be together in this way, right? And this way being that one of the even number, the smaller even number matches up with the larger number, right? So here, maybe you can say, you know, like, this is 4x and this is 4x plus 1, and they match, right? So that's going to be the case if you have no, if every number is duped. And then what happens when you take one away? Well, when you take one away, that means that, well, this probably is no longer true, what we said, because now this is now, I don't know, 4x minus 1, and then 4x for this one, right? And of course, then the question is, okay, where does this probably begin and where does it stop? Well, it stops at exactly the number that we're looking for. So there you go. I think that should be good enough to kind of find yeah, I mean, that's enough for you to do binary search, because then here you can see that, okay, if this probability that we just said is true, then that means that the unique number is to the left, otherwise it's to the right. And of course, if you there's some special cases that you have to check for. I mean, like if you're looking at 2 and the 3, that means that one of them is unique, and you can also just, you know, look at the number next to it or something like that. So we can get started already. Let's see. Let's say n is equal to length of nums. And of course, this is going to be an odd number by definition. You know, they don't tell you about it in the constraints, but and therefore, we can search for pairs starting on n over 2. There are different ways to implement this binary search, so it's up to you. But then here, then n plus 1 is going to be even. And then maybe I'm just going to write n2 for kind of like n half almost. Maybe I'll just write n half then, right? Is equal to n, oh, whoops, divided by 2. So by definition, this will be a whole number, right? So yeah. And then now we can do our regular binary search. We start from 0, right is equal to n half, yeah, inclusive, right? Let me double check whether that's true. And the way that I double check whether my bounds are, so first of all, this is inclusive bounds, and what that means is that we have left and right inside the search range, and both left and right are possible answers, right? So basically, that's the definition I usually go with. Some people like it exclusive. Do whatever you like, right? Okay, but is this off by 1 or not? So the thing that I would always do is just plug up in some real numbers to play around with. So let's say n is 9. Actually, in this case, this is 9, right? So let's just take this one. So let's just say the n is 9. nope. N is 9, then n half is gonna be 5, and of course that's not actually true because then we just want this 1, 2, 3, and 4. So that's not actually true. So this is gonna be n half minus 1, right? Because we want it to be on 8. We might have to handle some weird things differently, but that should be okay. I think we might have to. Yeah, we might have to think about things a little bit differently. So we might actually be able to rephrase this in a more precise way, which is that given the number here and the number that's bigger than it, if they're different, I mean, you could check this is the same as we said before, but maybe you can just add different if statements. But for example, if you had this 3, then we can go to the left because that's going to be true for every number until we see the number, right? So the first case in which the index is different from the index to the right should be good. And then of course then here, then we have to check the last case in a weird way. So what I can do actually is just check that ahead of time, right? So now we can do n over 2. So then we just skip this one. But of course we have to check n half over 1. So that means the last number, if num sub, the last number is equal to num sub, if this is not the case rather, of course length can be 1, so we have to double check for that. But if this is not the case, or if length is equal to 1, or this, we return the it's sorted, so the last number, right? I was thinking whether it can be either this one or this one, but this one doesn't make sense because then that means that by pigeonhole, the last number has to be that. Okay, so then now we eliminate this part. Now we can get rid of the last number, and then that makes our problem a lot easier. I mean, just easier to write, and yeah. So then now because we have an inclusive range, so that means that if left is equal to right, then the inclusive range would have one number, and that one number is your answer. So that's why I like to kind of explain it this way. And then we just have regular middle stuff. I write it this way to keep it simple. And then now what's good, right? So now the mid is one of 0, 1, 2, and 3 in this case. So that means that with num sub 2 times mid, and okay, let's actually write a good function. If good, where we'll define good. I like the abstraction just so that I can explain this a little bit clearer, maybe. Okay, look at the x pair of numbers. Return whether they are the same. I don't know. Yeah. Let's also rename this to same, maybe. I don't know. Naming is hard. Okay, so if they're the same, that means that the answer is to the right. So going to the right means that we want to move the left bound up, and moving the left bound up also means that the mid is not a possible answer anymore because mid is the same, so mid is not a possible answer. So that's how you get the left is equal to mid plus 1, because we eliminate everything to the left of mid. And then else if this is a possible answer, but we want to forward everything to the right, so therefore right is equal to mid. And I think that should be good. So then at the very end, left is equal to right, and it's also the index in which contains our answer. So that should be good. And of course, you can also prove to yourself that this is always the answer, or the answer always appears in, I guess, the even number indexes from 0, 1, 2, and stuff like that, because everything's sorted. So you could maybe do some proofs on your own, maybe homework. Yeah, hopefully I don't make a mistake. What happened here? Oh, I forgot to write the same part. Oops. So so we return this is equal to right. So this is just mapping it from the x pair to the actual index in the input, right? So okay, whoops. Let's give it a spin. Looks good. Let's check let's check smaller numbers, and also check like the first number. And I think that's probably most of the cases. So let's go. Let's see. Looks good. So let's give it a submit. Apparently I've done it twice before in 2 different languages. Not this time though. And there you go. 599, almost 600. Let's see how I did last time. I'm always curious how I did last time. I guess I did it the same. Or same idea. I mean, I guess it's only binary search, but this is more awkward. But yeah, this is also something that maybe I probably have a video on this from a previous time, so check that out. And then not only for whatever reason, but also so that you can kind of see how I evolved as a YouTuber, teacher, whatever you want to call it, and how I evolved my thinking on binary search as well. Because binary search, to be honest, is something that I historically was maybe a little bit weaker on, but I have gotten better over time just from sheer practice and a lot of volume. So let me know what you think. Even though I think this one was already better than I really used to be, but and you can kind of see like the choices that I make now in this video to make it so that this code looks even cleaner than last time. I mean, I think this other code is not entirely dirty or whatever. It's not like a mess, but there's still more if statements and whatever. But now that we kind of got it to here, you can see that this is much cleaner, right? I mean, of course I have some like thingies here, comments, but without the comments you can see that this is actually way clearer that I'm able to identify. And I want to be clear, I do not remember this problem at all, because I don't know, I don't, it's not worth my energy to remember these problems because it's just like silly one-off type things. But you can kind of see how maybe different my opinion is or whatever as well. But just to finish this up, this is going to be a binary search. We binary search on n, so this is going to be log n, of course, and of course constant space because we just have a couple of variables here and there. But yeah, that's all I have for this one. Let me know what you think. Hit the like button and the subscribe button, join me on Discord. Hope y'all have a great weekend. Happy Friday, happy Saturday, happy Sunday. Stay good, stay healthy, to good mental health, and take care. Bye-bye.